All right, you guys, welcome to Advanced Geometry Virtual Learning. Today we're going to talk about indirect measurements. All right, so sometimes you may want to know a measurement of something, a length of something, height of a flagpole, height of a tree, something like that you cannot measure directly, meaning it might be hard for you to climb to the top of that flagpole and run a tape measure down to the bottom, and so forth and so on. So that being said, we use indirect measurement to find the length. So let's do a couple examples. It's just based on similarity. It's pretty straightforward. So first, suppose Alex is 5 feet 3 inches tall. Now the very first thing I'm going to do here before I even go any further is I'm going to think about this and put it on the feet. 3 out of 12 inches is 0.25 feet, or a quarter of a foot. So he's really 5.25 feet tall. All right. And it casts a shadow that's 6 foot long. So shadow, you guys, is cast still on the ground, meaning, there's a sun up here. He's blocking out the sun's rays, and there's a shadow cast on the ground that's 6 feet long. Nearby, there's a lamppost, and its shadow is 18 feet long, and we want to know the height of the lamppost. All right, so we can figure this out, and this is something you could really go outside and do today. If it's nice and sunny out, take a tape measure. And, I know you've been dying to know the height of that tree next to you. Well, you can go figure it out by using this strategy. So, first things first, we got to have similar triangles. And the reason these triangles are similar is, one, look at this guy's incredible posture. He is for sure perpendicular to the ground. And this flagpole was built in a structurally sound way, so it's also perpendicular to the ground. All right, the other thing is that because it's the same time of day and these situations are right next to one another, then the angle of elevation to the sun would be exactly the same, which means that this angle would be congruent to that angle. So are the triangles similar? They absolutely are similar, and they're similar because of angle similarity. All right, next we're going to set up a proportion, and we're going to solve. All right, so just like when we had any other similar polygons, the way we set up our proportion first is to find a similarity ratio. My similarity ratio, I notice that I know that this is 6 and this is 18. So the similarity ratio from the small triangle to the big triangle is 6 to 18, or 1 to 3 when you simplify it. So I find a similarity ratio, and then I can set up a proportion. I'm going to say 1 over 3 is equal to 5.25 over x. And then when I cross multiply that, I'm going to get 1 times x is x, of course. And then 5.25 times 3 is 15.75. So we know that flagpole is 15.75 feet tall. Now, let's make this answer a little bit more reasonable and kind of like what we had in the beginning. 0.75 feet. Well, 0.75 times 12 inches in a foot gives me 9. So that flagpole is 15 feet and 9 inches tall. Boom. All right. Again, pretty easy, pretty straightforward if you understand the concept of similarity. Now it's just drawing a picture and setting up similar triangles. Let's take a look at another example. All right, so this is the same thing, but in this time I just wanted you to practice drawing your own picture. So you have a 40-foot flagpole and its shadow is 25 feet. All right, so let's draw this. Here's my ground, perfectly straight. All right, I got a 40-foot tall flagpole. All right, this is 40 feet. And its shadow, remember you guys, the shadow is along the ground. The shadow is 25 feet. And then we'll make this nice triangle like we had in the previous problem. All right. And could have drawn a little straighter, but we get the point. All right, and you got a nearby building, and it's 200 feet tall. We want to know the length of its shadow. All right, so here's my giant building. All right, find the length of the shadow. It's 200 feet tall. Its shadows along the ground. And we want to find the length of the shadow. So again, these triangles are similar because you got right angles, and the angle of elevation to the sun is the same. So they're similar by angle-angle similarity. Therefore, I can set up a proportion and I can solve. First step is to establish my similarity ratio. So I know both the heights. Those are my corresponding lengths. All right. Now, when I simplify 40 over 200, you end up with 1/5. All right. So my similarity ratio is 40 over 200, which is 1/5. Cool. And so from there, I can set up my proportion. So I'm going to go from small to big. So 1 over 5 is equal to 25 over x. And then when I cross multiply, I end up with 1 times x is x, and 5 times 25 is 125. So I end up with the length of the shadow is 125 feet. Booyah. Again, pardon my terrible handwriting. All right, last example. All right, this is very similar, just uses another way of setting it up. You can do this using a mirror. And you guys may have learned in physical science that when you reflect something, there's two angles that are formed. So first of all, this represents my little mirror down here. So what's happening here, right? Let's start there, I guess. So on a trip to Mexico, Emerson eagerly wanted to know the height of this flagpole. He was dying to know its height. Thankfully, he always brings with him a mirror and a tape measure, so he could use an indirect measurement strategy he learned in advanced geometry to find the height. Now, if we draw a perpendicular line to this mirror, in physics or in physical science, your teacher may have called this the normal line. Normal in math means perpendicular. All right, when you guys learn about vectors in math classes to come, you learn that normal vectors are perpendicular. So I draw this normal line perpendicular there. Now what I know is that the angle of incidence, is what this angle is equal to what's called the angle of reflection. And that's always true when you're reflecting something off of a mirror. So because of that, and because this is perpendicular, that means that these two angles will also be congruent because they're complementary, and if these are the same, then these will be the same. And furthermore, this guy has excellent posture. Emerson, nice work. That's perpendicular to the ground, and the flagpole is perpendicular to the ground. So those two triangles are similar by angle-angle similarity. All right? So here's my setup. All right? Let's just draw it using segments here so we can solve it. All right, that's representing Emerson. There's the ground. This is my flagpole. And here's my little angle of reflection. All right, so I know that that angle, and this is what, point P, E, X, B, and F. I know that they got right angles, and I know that these angles were congruent. And I know, let's see what else I know. I know the distance from the ground to Emerson's eye is 5 feet 9 inches. So same deal, 9 inches is 9 out of 12 is 3/4. That's 5.75 feet. All right, the distance from Emerson to the point of reflection on the mirror is 4 feet. And the distance from the base of the flagpole to the point of reflection on the mirror is 8 feet. We want to find the height of the flagpole. So again, we'll set up first our similarity ratio. And what we have there is we have that this is 4 and this is 8. Those are the corresponding sides. You'll notice they're both between the two marked angles. And as you guys all know, 4/8 simplifies to 1/2. So there's my similarity ratio. So from the small triangle to the big one, I say 1 over 2 is equal to 5.75 over x. All right, when I cross multiply, 1 times x is x, and 5.75 times 2 gives me, what, 11.5. So 11.5 feet, or half a foot is 6 inches, 11 feet and 6 inches. There you go, Emerson. You figured out the height of the flagpole. I'm so proud. All right, guys. I hope that was as entertaining for you as it was for me. Hope you're having a great day.